Okay, good evening. So, this is our 20th lecture, and if you recall from the previous lecture, then we have started discussion on the ellipsoidal fluid particles. Okay, and specifically, if you recall, we have already talked about the terminal velocity and the drag coefficient for ellipsoid fluid particles. So, now we will have a very brief discussion about the shape of the ellipsoidal fluid particles, and then we will move to another category of fluid particles which are but nothing but the particles of size more than the ellipsoidal fluid particles, and these are called as deformed spherical caps. Okay, so in terms of ellipsoidal fluid particles, if we have to determine the shape of the fluid particle, then of course whenever we discussed the stationary fluid particles resting on a plate, then we have seen that if it is on a either horizontal plate or it is on a inverted plate. In both the scenarios, our under the static conditions, this hydrostatic pressure was being balanced by nothing but the surface tension pressure. Okay, so this is something which we have seen. But when the fluid particles are not stationary but these are in motion, then there will be some other pressure because of the hydrodynamics, like because of the motion of the fluid particle. So whenever we are writing the pressure balance across the interface, we have to consider that additional pressure because of the motion as well. Okay, so that's why here I have written this PhD and PhD in particles. So it means this is additional pressure in the continuous liquid because of the fluid motion, and this is additional pressure in the within the particle due to internal circulations present within the particle. Is this point clear? So once particle is having fluid motion, then fluid motion will also be generating certain pressure, and that pressure actually we have to account for. And of course, whenever we will be seeing the balance of this particular equation, then only we will be able to predict the shape of the fluid particle. So ultimately, this is the equation, but the shape of the fluid particle becomes a bit complex, so that's why it is extremely challenging to specifically identify the exact behavior of the shape from the theoretical analysis. So majority of the findings are actually based on the experimental data. Okay, so in terms of experimental data, this aspect ratio E bar, so here you can see this aspect ratio is plotted as function of Edwards number of the bubble. Okay, and here you can see that we have these different lines, and these different lines are corresponding to different values of Morton number. Okay, so here you can see this Morton number value for this line is 10 to power minus 6, then for next line is minus 5, minus 4, minus 3, and likewise we are increasing the order of the Morton number. Okay, and ultimately we know that when Edwards number is, when EO is greater than 40, then shape regime shifts from ellipsoidal to the spherical cap. So this particular zone over here is nothing but corresponding to the value of spherical cap regime. Is this point clear? So here shape is not now ellipsoidal. And another interesting point is, if you see any particular value of the Edwards number, and then if you increase the value of Morton number, then ultimately what is happening, there is less deformation in the shape of the droplet, because for a given Edwards number, if we increase the Morton number, then value of aspect ratio is coming closer to 1. So if it is coming closer to 1, it means upon increasing the Morton number, deviation in shape from the spheroid is actually less, and for low Morton number value, deviation from the spheroid shape will be actually highest. Typically for Edwards number less than 40 and Morton number value less than equal to 10 to power minus 6, this is the empirical equation with which actually you can predict the shape of the particles. So you can predict the aspect ratio. So if you are able to predict the aspect ratio, it means you are knowing that what is the extent of the ellipsoid present in the system. Okay, and typically, so this is to very specific condition of Morton number, like very small values. But in moderate values of Morton number, which are less than 10 to power minus 3, what we can do, we can have another dimensionless factor Ta, which is equal to Reynolds number times Morton number 0.23, and for different values of Ta, this is how actually we can predict the aspect ratio. Okay, so it means we can give some information about the shape of the bubble, and majority of this information is nothing but estimated from the experiments. Okay, because there is no theoretical evidence present for this. Then similarly, this is about, so in the previous section if you see, these were shapes of ellipsoidal fluid particle. It means these are in terms of dimensionless parameters, so we are talking about the general behavior of the fluid particles. And in the next slide you can see deformation of drops and bubbles, but specifically we are talking about presence in surrounding fluid, which is nothing but a pure water. Okay, and in the system you can see this is the aspect ratio, and in the abscissa we have with Gauss number times 1 plus 0.15 into k divided by 1 plus k, where k we already know that it is nothing but ratios of particle viscosity to the continuous fluid viscosity. So here you can see the experimental data, and particularly you can see that for values of k equal to 0, k equal to 1 and k equal to 2.5, this is some equation which is fitted over here, and here you can see that your experimental data is actually, whenever this particular parameter is increasing, then this experimental data is completely deviating from this equation. Okay, so another interesting point is, whenever we have ellipsoidal shaped particles, then we know that behind the particle there will be formation of wake. Okay, so in terms of spherical particle, this wake structures are studied in very much detail, but for ellipsoidal fluid particles you will be finding 5 different types of behaviors. So here, this first type of wake structure you can see, this is the non-oscillating nitrobenzene drop, and corresponding to this we have nothing but steady thread like laminar wake. So here you can see this is nothing but a smooth thread which is just attached to the particle. Okay, so this will be applicable when your equivalent diameter is 0.28 centimeter and Reynolds number is 515. Once you increase the equivalent diameter and the Reynolds number, then again you are having steady thread, but this is accompanied by toroidal vortex wake. So here you have this thread like structure, but here you have some circulation also. So it means thread like structure accompanied by some toroidal vortex. But in both these situations you can see the shape of fluid particle will not be deforming. Shape of fluid particle will remain as it is. Okay. On contrary, if you further increase the value, if you just consider another situation, so this was M nitrotoluene drop, but if you consider nitrobenzene drop of almost same conditions, same diameter and same Reynolds number, there you will be finding you have oscillating drop. So oscillating drop means, what I told in the oscillating regime, what happens earlier also I told you, that say now shape is like this, then after some time shape may be like this, then after some time shape may be again like this. So we will be having so many oscillations in the shape of the fluid particle. Okay, so here you can see when these oscillations are there, then we are having a central thread. So this is nothing but a central thread, here you can see, and then outside this central thread we have vortex sheet roll. So this is a big thin sheet of vortex. Okay, so if you rotate this, this will be becoming a thin sheet of vortex, and this sheet is rolled inward to give inverted bottle shape. So this seems like nothing but a bottle, just you have put in the downward direction. Okay, and Further increase of diameter and Reynolds number, you can see here vortex seat which was there in case of C, it has actually broken to form vortex rings. So here you have number of vortex rings which are shedded behind the particle. Okay, and here you will be having again oscillating shape. Okay, and further increase of Reynolds number, again you have oscillating shape, but now whenever this vortex shedding is happening, in case of D this vortex shedding structures were symmetric, now you have a symmetric structure, alternate asymmetric structure. So one is shedding towards one side, then towards the other side. So alternate asymmetric structure we will be having. Okay, so you will be finding in majority of these non-oscillating regimes you will be having almost smooth and steady motion of the particle. Okay, on contrary, when you will be having the shedding of the vortex and shape oscillations in the fluid particle, then your motion will not be straight. Either you will be having spiral motion, or you will be having rocking like reciprocating motion, or planar zigzag motion. Okay. Then if you have to see the nature of shape oscillations, then again there is no theoretical analysis which is available, but what people have done, people have actually tried some spring damper analogy in order to determine the shape oscillations theoretically. So one thing can come to our mind that typically the oscillations are coming in the shape of the fluid particle when vortex is actually shedding. Okay, so one thing intuitively can come into our mind that the frequency of the oscillations of the shape can be equal to that of frequency of vortex shedding. Okay, but whenever people have done experiments, it was found that these two frequencies were not same. Okay, so typically if you say that Fw is your frequency of vortex shedding, so Fw is nothing but frequency of vortex shedding, and Fn is natural frequency of the droplet. So natural frequency of the droplet will be depending upon its density, viscosity and surface tension, etc. So that is something which is calculated over here. And then if you calculate some frequency F bar, which is Fw plus Fn by 2, and one frequency delta F, which is Fw minus Fn by 2, then typically the deviation in the shape of the bubble, so E bar is nothing but mean aspect ratio. Okay, so when your bubble is oscillating, you will be having different aspect ratio corresponding to each and every time instant of the bubble shape. Okay, so if you take the mean of all that, and if you calculate instantaneous aspect ratio minus mean, that can be proportional to F bar by delta F sin 2 pi delta Ft and cos 2 pi F bar T, where cos 2 pi F bar T represents the frequency of, like this F bar is nothing but frequency of shape oscillations, and this delta Ft term is to account for oscillations in amplitude. Okay, understood? Oscillations in amplitude. So maybe if you know little bit about compressibility effect, then you will be able to relate this much, but of course you need not to go into many deeper details, because whatever this theoretical analysis is there, it is not matching with the experimental data. This is just to show the nature of the oscillations, that how this trend is actually seen. So here you can see this is nothing but F bar frequency. So this is corresponding to the shape oscillations, and this is corresponding to oscillations of the amplitude. Okay, so typically if you see your pressure waves in case of your acoustic systems, there you may have this type of combined waves present. Okay, so if you see the flow transition for bubbles and drops in liquids, then we have seen that if we are having 100% pure system, then we will be having circulations present inside the bubble, and smallest shape will be spherical, and once size increases, then we will be moving towards the ellipsoidal regime. Okay, and if I have this impurity is less. So impurity is less, then my spherical fluid particle will be remaining in the form of a rigid particle, because internal circulation will be vanished. Okay, and then both these rigid particles and circulating one, particularly in which regime? Particularly in ellipsoidal regime, will be deformed circulating if impurity level is less, and it will be deformed rigid structure if impurity level is high. Okay, and finally all these nothing but enters to a single regime which is called as oscillating bubble, and in case of oscillating bubble there is not much effect of the surfactant. Okay, so if you recall from the previous lecture how we were having the velocity profile, first a unique data in spherical regime, single line, then line was deviating in the ellipsoidal regime. So one was for pure system, one was for impure system, and finally when the size was becoming large, then again the data was actually merging together. Because when you are having oscillations present, then ultimately oscillations also dampen the internal circulation. So typically the nature of oscillations is to dampen the internal circulation of the fluid. So if oscillations are dampening out the internal circulation, surfactant is also doing the same thing. So whether surfactant is present or not present, ultimately your internal circulations are damping out. So if internal circulations are damping out, it means your only shape oscillations are there and there is no internal motion. So that is irrespective of the presence of the surface we will be having. So that's why ultimately we will not be finding any any effect of surface contamination. Okay. Now let's talk about the next category, because we have seen that once we go to the value of Idvos number greater than 40 and Reynolds number greater than 1.2, and typically the diameter of the fluid particle greater than equivalent diameter of fluid particle greater than 1.8 centimeter, then we have nothing but our, in that case we have, yes, we have larger shape fluid particle, and this is the shape, and this particular shape is actually called as spherical cap shape. So why spherical cap shape? Because if this is a sphere, if you take the top portion of the sphere, so this is nothing but cap of a sphere. So that's why it is called as spherical cap, and typically this spherical cap shape is having one interesting angle. So if you see this is nothing but the complete sphere. Okay, so if from the complete center of the complete sphere, if you measure this particular angle, theta w, okay, so this theta w angle is actually very, very important, and it is called as wake angle. For spherical cap shape, this angle is important and it is called as wake angle. So here, the way we were having earlier aspect ratio, here also we can calculate aspect ratio, but majorly up to what extent actually this sector of sphere is extending, that is defined by the wake angle. Okay, and if you see the value of wake angle, then this is the Reynolds number of the particle corresponding to terminal velocity. So ut over here is terminal velocity. Okay, so this is Reynolds number. At very low value of Reynolds number, your angle is actually very large. Okay, once your Reynolds number is increasing, then you will be finding this angle is actually decreasing. So ultimately this point is kind of considered as the transition from closed wake to open wake. In case of closed wake, you will be finding shape something like this. So this particular extent, this will be extending somewhere close to here, then only you will be getting larger angles. Okay, but in this case, this is somewhere here, so this is nothing but a open. Okay, we have to see that this particular shape is mostly shown by only gas bubbles. typically in case of droplets you will not be experiencing this shape. Why? Because whenever a droplet falls down, and if this is of that much larger size, of course the surrounding fluid viscosity will be less. So vortices forming in the surrounding fluid will be of more strength, and these will be actually breaking the droplet into smaller entities before the Ugo's number 40 is achieved. Is this point clear? So this is one important point, that the spherical cap characteristic is majorly shown by gaseous medium. It is not shown by the liquid heavier medium, because in case of liquid medium you will be finding that the particle viscosity will be larger and the surrounding fluid viscosity will be less. So if surrounding fluid viscosity will be less because of the large size of the particle, there will be stronger wake formation, and this stronger wake in the low viscosity surrounding fluid will actually deform particle in such a way so that it is breaking into smaller entities. So that's why in case of liquid particles you will not, particularly in case of droplets, you will not experience the spherical cap shape. Okay, and when Reynolds number is greater than 150, typically base is flat and wake angle is close to 50 degrees, and when Reynolds number is less than 40, so in this regime, then you will be finding that base is having some oscillatory dimpled structure. Okay. And if you talk about the terminal velocity of the spherical cap bubble, so first what is done, this is the balance of pressure. Okay, so if you have this bubble, then here you can see any value of pressure measured at the surface of the bubble is called as surface pressure Ts. Okay, and the value of pressure which is measured corresponding to theta equal to theta w equal to 0, wake angle equal to 0. So corresponding to theta equal to 0, whatever the value is, that is called as P naught. Okay, so Ps means pressure at any point on the surface of the bubble minus pressure corresponding to peak point is equal to, this component is coming from the gravitational head and second component is coming from the velocity head. So say if ut is terminal velocity of the bubble, then this is the gravitational pressure change and this is pressure at the surface because of the motion. Okay, and once Reynolds number of particle is greater than 150, corresponding to that we can assume that the boundary layer forming across the surface of the bubble is very thin, and majorly we can estimate pressure drop from our potential flow analysis. So velocity will not cause any pressure, so majorly pressure will be coming because of the gravitational head. So that is what is done over here. So rho p g a into 1 minus cos theta, where a is nothing but radius of the sphere from which this spherical cap is actually extracted. Okay, and once you balance these two pressures, then you get nothing but the value of terminal velocity. Okay, and typically for Reynolds number greater than 150, value of theta is close to 50 degrees. So if you substitute this, then you will be getting your ut equal to 2 by 3 Ga delta rho by rho. Okay, and up to this point, is it clear? So further, if you have to account for effect of aspect ratio of the bubble. So aspect ratio of the bubble means, say if your spherical cap is like this or spherical cap is like this, so then you will be able to account for this aspect ratio as different value, this aspect ratio as different value. So this is one theoretical relation, and second is, if you have to account for the effect of this aspect ratio, then actually you can finally calculate the value of ut as 0.652 into square root of Ga bar delta rho by rho, where A bar is nothing but average radius of curvature only when value of theta is taken within the range of 0 to 37.5 degrees. Okay, so what you can see that whatever the two different values of velocity are estimated, these value of velocities are nothing but matching well with the spectrum of the experimental data obtained from different resources. Is this point clear? So all these dotted points are nothing but experimental data from different sources. So these values of terminal velocities are actually matching well with this experimental data. And then of course you can calculate the terminal velocities and drag coefficient in different regimes depending upon the different values of Reynolds number and Gauss number. So I will not go into these details because these are nothing but all empirical relations driven from the experimental data. Okay, so there is no theory involved in these relations. Okay, and this is the surface pressure distribution. Again, this surface pressure distribution is also actually coming from fitting of the experimental data. So these dotted points are nothing but experimental data, and using these two relations you can actually fit the surface pressure distribution for this type of bubbles. Okay, now comes another important category of spherical cap bubbles, which are called as skirted spherical cap bubbles. Okay, so in case of skirted spherical cap bubbles or droplets, what happens, you will be finding that behind the spherical cap there is formation of a thin annular film. So this is thin annular film, and within this thin annular film you will be having the continuous phase. Okay, so this type of bubbles are nothing but called as skirted bubbles. Okay, so skirted bubbles are typically observed when Reynolds number is greater than 9 and ratio of Weber number by Reynolds number is greater than this particular value. And skirted shapes will be observed for drops. So skirted shapes are observed in case of drops also. So in case of drops, if Weber by Reynolds number ratio is greater than 2.3 and Reynolds number is greater than 4, then you will be finding the skirted shapes. And typically 5 different types of skirted configurations are observed. So one is called as smooth skirts curled inward. So whatever I have drawn over here, this is nothing but a category 1. If you have straight skirts perpendicular to the base of the bubble or drop, so it means if this base thin film is becoming straight at the trailing edge, then we will be calling category 2. If this is having some wavy structure, then this is category number 3. And once these skirts are actually folding out and breaking further, then we call this exfoliating skirts and fluttering skirts. Okay, so depending upon the shape you can actually classify each type. And one important point is the transition at which these fluid skirts are actually formed. You can classify this in terms of capillary number or skirt number. So ratio of Weber number by Reynolds number, which is mu into u terminal velocity by sigma, this is either called as capillary number or skirt number, and this is when it is plotted as function of Reynolds number. So here you can see this particular zone where you are not having the presence of any skirts, and above these values you will be having the formation of skirt regime, and this transition can be calculated based on this particular equation. Okay, so this equation is fitting this data and it is giving the separation in between the skirted regime and the non-skirted regime. Okay, so all these are nothing but driven from experimental data, and then you are actually fitting into these equations. If you have skirted bubbles, then of course skirted bubbles are having some internal circulations. So if you see the data of internal circulation, so this is one big main vortex, and then you can have small secondary vortex which will be very weak. Now presence of this weak secondary vortex is something which is not observed in experiments. But why this particular vortex is shown in the reverse direction? Just to balance the tangential stress condition at the boundary. So theoretically tangential stress should balance at the boundary. So that's why if in the surrounding fluid some toroidal vortex is forming, here also we should have vortex formation in the opposite direction to the main vortex, then only our tangential stress condition will be balanced. So if you have to see, this small weak thin secondary vortex is something which is not observed experimentally. Experimentally people have observed only this big vortex profile, but this small vortex is hypothesized from the theoretical consideration, because in secondary fluid also we are experiencing some toroidal vortex. So if with this toroidal vortex we have to balance the tangential stress at the interface of the bubble, then theoretically there should be some presence of secondary circulation. Then only tangential stresses will be balanced. Because if tangential stresses theoretically are not balanced, then shape will not remain same. Okay, so that's why this is theoretically hypothesized. It is not experimentally observed. And also very less amount of work is done to experimentally characterize these vortices. So very less number of studies are there. And if you have to see the wake size, so then volume of wake divided by volume of bubble is plotted as function of Reynolds number, and here you can see when the Reynolds number increases, these values are increasing, and these plots are nothing but log plots. So that's why you can fit this data with the help of power law relation. Okay, because this side also you have log scale, this side also you have log scale. So you can fit this particular wake volume data with the power law profile. So one important point is, whenever you will be increasing the Reynolds number, then formation of the wake volume will be actually increasing. Okay, and this is the external flow field for different values of Reynolds number. So of course outside the wake you will be finding at smaller Reynolds number this is your wake, and at larger Reynolds number this is your wake volume. So it means when the Reynolds number is increasing, your volume of the wake is actually also increasing. Okay, now comes one interesting aspect. So till now whatever the analysis we have done, that is corresponding to the presence of fluid particles in infinite surrounding fluid. Okay, but in reality you will be finding that surrounding fluid will not be always subjected to infinity, but you will be having say small vessel. Inside that vessel if you have fluid present and there you are having the dispersed fluid particles, then your fluid particle will be influenced by the wall also. Okay, so that one configuration is shown here. So here you can see this is nothing but a simple circular pipe or tube, and in this tube flow is happening from bottom to top, and in this tube we know that this is nothing but a Poiseuille flow situation. So in case of a Poiseuille flow situation, under laminar flow conditions our velocity profile within the tube will be laminar. Okay, so in this laminar velocity profile at the center of the tube we will be having highest velocity u0, and as we shift towards the wall, parabolically value of velocity will decrease and at wall it will become 0. Okay, and this is the diameter of the tube. This is the radial direction measured from the axis of the tube, and here this is direction I, so flow is happening parallel to ith direction, and here I have a spherical fluid particle or solid particle, it can be any. So I have a spherical particle present within the flow field, and this spherical particle is moving in downward direction with velocity u. Okay, so this is the configuration. So if you see what was happening previously, whenever we studied the spherical particle, at sufficiently away from the spherical particle everywhere velocity was u naught. But now here you can see when you are even moving sufficiently away from the fluid particle, you are having some variation of velocity. Parabolic velocity profile is there. You don't have the constant value of the velocity. Okay, so that is something. This is the change which will be happening in theoretical analysis. Now, if I consider the analysis the way we have done previously, that if I fix my reference frame on the particle, if I fix my reference frame on the particle, then what will be happening? All the things, surrounding things will be moving with reference to the particle. So now you can see in my actual configuration, this particular wall is at rest and particle is moving in downward direction. So with reference to particle, what will be happening? Wall will be moving in upward direction with velocity equal to that of the particle velocity. So that's why in my velocity formulation I can write u vector is nothing but ui at walls. Is this point clear? All are clear with this idea? And secondly, if you have to calculate velocity at any point of time, so velocity at any point of time will be nothing but u, which is your wall velocity, plus u naught into 1 minus r square by r square. Is this one clear? And third important parameter is lambda. What is lambda? Diameter of the particle divided by diameter of the confined system. Okay, so diameter of pipe over here. And fourth important parameter is B. What B is representing? Eccentricity. So this is nothing but the distance of center of particle from the axis of the confinement. Okay, so because if your particle is just falling at the axis, then always it will be experiencing the maximum value of velocity. Whenever it will be moving away from the axis, then value of velocity will keep on decreasing. Okay, so that's why eccentricity is also important parameter. Okay, so typically under the creeping flow regime, what is creeping flow regime? In the creeping flow regime, if you invoke all these boundary conditions, by invoking all these boundary conditions, you can theoretically calculate the solution over a sphere. But if you go beyond creeping flow regime, then finding solution will be challenging, because then this wall effect will be also contributing much. Okay, in creeping flow regime, only this velocity profile will make the major effects. So that's why few important things we will be seeing. If we have, say, rigid spherical particle, so rigid spherical particle means either I can have solid sphere or contaminated, yes, contaminated fluid particle, or I can have fluid particle of large K. Okay, fluid particle of large K is also not having any internal circulation present. So if any of these three situations are existing, then we will be finding that onset of separation will occur at 20 times 1 minus lambda minus 0.56 for values of lambda less than 0.8. So we all know when we were having spherical particle, we said that flow separation will start appearing at Reynolds number close to 20. Okay, but in this case, this flow separation will be affected by the value of lambda. Okay, so onset of flow separation is now a function of lambda as well. Okay, then second point is limit for Stokes flow. So Stokes flow is applicable when our Reynolds number is less than 1. Okay, so in this case, when wall is present, then limit of Stokes flow is also changing, and limit of Reynolds number up to which Stokes flow assumption can be applied, this limit is actually given over here. Is this point clear? So typically for Stokes flow we say that Reynolds number is less than 1, but here this limit will be actually modifying. Okay, And third, three important factors we will be defining over here, and with the help of these factors actually we can correlate the correlations of drag coefficient and terminal velocity from that of unconfined system. So first is called as drag ratio, Kf is called as, so drag ratio is nothing but ratio of drag force in bounded fluid, our actual situation, divided by in infinite fluid where there no walls are present. Second is Ku, Ku is terminal velocity in infinite fluid divided by terminal velocity in bounded medium. Okay, and third is K mu, K mu is called as viscosity ratio. What is the meaning of this viscosity ratio? Mu s by mu. Mu is our actual viscosity of the surrounding fluid, and mu s is the viscosity of the surrounding fluid assuming unbounded flow, which is giving the same value of terminal velocity. Is this one clear? So in unbounded medium your terminal velocity will be different, in bounded medium terminal velocity will be different. So you have calculated the velocity of value of terminal velocity in bounded medium, and corresponding to same terminal velocity, if you consider that you have unbounded scenario, and then if you just keep on changing the value of surrounding fluid viscosity, which will be giving you same value of Stokes velocity, that viscosity we are calling as Stokes viscosity. Okay, so this is called as Stokes viscosity, and the ratio of Stokes viscosity by actual viscosity is called as viscosity ratio, and of course the Stokes viscosity can be calculated from this value of terminal velocity which is available for Stokes result. So this ut I will be nothing but substituting simply for terminal velocity in bounded result, and this will be then giving me Stokes viscosity. Okay, and all these factors are equal to 1, these are same if I have creeping flow situation. As I told you that in case of creeping flow situation, surrounding walls are not affecting much, and if we simply do the theoretical analysis by just considering the parabolic velocity profile, I can calculate all the values. So that's why all these factors will be actually coming equal to 1. But if you increase the Reynolds number, so typically for low Reynolds number cases, value of K can be calculated using these relations, and here you have this C as one coefficient, and this C for different configurations, the values of C are given over here. Okay, so first configuration is, for example, circular cylinder. So it means fluid particle is present in a circular cylinder, and location of particle is at axis of the cylinder, and direction of motion of the particle is axial. Then you will be having value of C equal to this. If you have eccentric situation, so it means particle is not present at center, but it can be at any location along the radial plane, then corresponding to different values of eccentricity, value of C will be different. So that is what you can see this value in this particular plot. So here you have C and here you have B by R. So B by R is nothing but B by R close to 1 means we are approaching more towards the wall. Okay, is this one clear? So, and particularly for B by R less than 0.3, this is the equation with the help of which you can also calculate value of C if this diagram is not present. And if you have two parallel plane walls, so say flow is happening and this is confined by two plane walls like plane Poiseuille flow, and then you have particle present exactly at the mid plane and flow is happening parallel to wall, then value of C will be 1.00. So it means that simple is situation is, if you know the drag force in unbounded medium, terminal velocity in unbounded medium, just calculate the value of K and multiply it with these relations, you will be able to determine the values in the bounded medium. Okay, so that is the simple relation. Similarly, you can see more number of expressions for k. Now here, earlier the value of lambda was fixed. Now you are considering the effect of lambda. Okay, lambda means, considering the effect of lambda means considering the effect of diameter of particle and diameter of the tube confinement. Okay, so depending upon that you can have different relations. Okay, so you have to, I am just making you familiar with the relations. So if in the exam question comes, you should be able to decide that which graph is to use and which relation you have to choose. Okay. Then if you have high Reynolds number, then for Reynolds number in the range 1 to 50, drag coefficient can be written in terms of drag coefficient for unbounded medium plus 24 by Re into k minus 1, and value of k you can simply calculate from this previous table. Okay, and then kf for 100 to 10,000 and more than 10,000 you can actually calculate using these relations for different values of lambda. And if you see the value of CD as function of lambda, so here you can see this is your Reynolds number and this is the drag coefficient. So drag coefficient for different values of Reynolds number are actually, for different values of lambda are shown by these different lines. Okay, and one factor is also calculated over here, kf minus 1. So this factor kf minus 1 for different ratios is shown over here. What is the factor kf minus 1? What was kf? Drag force for bounded, unbounded by bounded. So it means kf minus 1 will represent the, yes, deviation, how much our drag force is deviating from the unbounded system. So the value of that factor depending upon the different values of lambda you can see over here. So deviation is least when value of lambda is small and deviation is actually increasing when value of lambda is increasing. Is this point clear? Then if you have high Reynolds number, then you can see the terminal velocity of the particle, particularly for b equal to 0. B equal to 0 means zero eccentricity case. Okay, zero eccentricity case. Particle is just lying at the axis. And ND, what is ND? Dimensionless diameter, as we have studied in the previous lecture. Okay, so here you can see for different values of lambda how terminal Reynolds number is actually varying, and then you have Ku minus 1 also. So Ku minus 1 means deviation in terminal velocity from unbounded flow. Okay. Then similarly this K mu is also given over here. So K mu is, so it means you can see that when your value of lambda is increasing, value of K mu is also increasing. It means for large value of delta, the amount of Stokes viscosity in unconfined system has to increase in order to give the same effect as that of bounded system. Okay, so all these are nothing but empirical correlations based on the experimental data. So why I am showing over here, because you should be familiar with this, and for more details you can read the chapters of this book Clift and Weber. So there also they have just provided summary of all these correlations. So why it is important? Because in the exam, if you are expecting some question, then you should be able to decide that which type of charts are to be used and which correlation is appropriate for your situation. So you should be just familiar with this, because this is not for remembering, this is just to get idea. And another important point is, whenever we have the presence of this type of system, say if we have this wall bounded system, then depending upon the inertia of the system, we can also have migration of the particle. Migration of the particle means particle will not follow the straight path just parallel to wall, but it can either come towards the center or it can go in outward direction depending upon the inertia of the particle. So right now, whatever discussion we are doing, we are assuming that we are operating in the steady regime, where particle is just moving at its terminal velocity. So it means it is an inertia free system. So that's why I am not discussing much about migration effect. But say later on, if we consider some particle with fluid inertia present in the system, then we have to also talk about the particle migration. So you can simply remember, if inertia is not present in the system, then there will not be particle migration. It means if particle is located at certain distance from the wall, it will just follow a straight path at that particular location. Okay. But when inertia of particle will be coming into picture, then it will not remain at fixed distance from wall, but it can migrate either to center or it can go to outer. Okay. So what happens with the presence of inertia, that we will see in the subsequent discussion. Today majorly we have talked about this wall effect for particles which are in spherical shape. So spherical shape particle, it means, and that too I have specifically mentioned rigid particles. So the meaning of rigid particle, three situations: either solid particle or large K value particle, fluid particle, or contaminated fluid particle. But of course you have to consider that the size of fluid particle is very small. So size is less than 1 mm, because when the size of the fluid particle will be greater than 1 mm, then you will not be having the spherical shape. Okay, so then shape of particle will change, and here we will be having the different system. Okay. Okay, so now
इस केस के अंदर वेग जनरेट हो गए सेंटर